Hello, welcome to Einstein Mechanics. Let's look at the application areas of thermodynamics. This will help us appreciate and understand how thermodynamics is useful in our daily activities. So the human body, we know that there are a lot of cells inside the body, about trillion cells, and in each cell there are metabolic activity that happens, and these activities generate heat. So this heat generated is either conserved or rejected, depending on the body temperature or what season we are. So it is conserved when we are in the cold season, and it is rejected when we are in the hot season, or depending on the activities we are carrying on at the moment. So if I need heat or if I'm feeling cold, I have to conserve the little heat generated by the cells by wearing heavy clothes in order not to have too much cold. That's the principle of thermodynamics. And if I'm working in a hot sun or a hot afternoon and I'm sweating, the heat generated in my body, I have to take off my shirt. I have to reject the heat inside the body. And you see, the regulation of this heat is application of thermodynamics, because we know that by the principle of thermodynamics, heat as thermal energy will move from our body to compensate for the atmosphere temperature. And when we put on heavy clothes, we know that since it is cold outside, our body will try to also compensate for heat outside. So we prevent that by wearing heavy clothes. Are we good? So even the body, we regulate our body temperature, that's heat energy, by the principle of thermodynamics, which is very interesting. And the second point, we know that in many households there was appliances, and these appliances, we have some as computers, we have TV, we have iron heaters, we have refrigerators, and air conditioning. They are all working on the principle of thermal energy. Yes, they convert electrical energy to thermal energy, and we know that as heat is generated in these devices, we must find a way to make use of it. So when you look at the iron, we make use of the heat energy, the heater and the refrigerator. Are we good? So all these devices are made based on the principle of thermodynamics. And remember, some are automatic. The moment the heat is in excess, they cut. Something like the iron, the fridge, even some water heaters. When the heat is too much, they have a regulator that will regulate it. And that is only made if you have knowledge in thermodynamics. Are we good? Thermodynamics also plays a role in the design and analysis of automotive engines, rocket, jet engines. Are we good? We have solar collectors and a whole lot. So if we want to make rocket engines, you cannot do it without application of thermodynamics. Because remember, these engines are going to get heated, and you will need what we call cooling systems. Are we good? You need cooling systems. So if you don't have that idea in thermodynamics, where a cooling system will be brought inside, and even what type of cooling system am I going to use on this particular engine, they are all selected and made based on thermodynamics. Are we good? Because some engines will need oil as cooling system, some will need water. We don't use oil as where water is being needed. So thermodynamics will help you understand the amount of heat generated in a particular engine and the cooling agent available, the cooling agent. So something like solar collectors, we know that the sun gives us solar energy, and we have to get collectors that will store this energy for future use. And thermodynamics helped us to achieve that, which is very practical. So we can see that thermodynamics is really important. We have energy efficient homes, something like we have energy efficient bulbs. Very good. Have you come across that before? Energy efficient bulbs that will what? Minimize the usage of what? Electricity, and it will cut down cost. Very good. And finally, the size, the location, and the power input of the fan of a computer is also selected after analysis that involves thermodynamics. We know that in computers, there are what? Fans. You have the computer fan for what? Cooling. As what? Cooling purposes. And we have to know the location where to place it in order not to what? Blow the heat back inside what? The computer. So selecting that depends on what? The application of thermodynamics, which is very, very useful. This and many more. There are many other applications of thermodynamics. Let's look at dimensions and units. Dimensions and units. You know, in engineering, we don't joke with our units. Any quantity you measure should come with its what? Unit. So here are the 7 basic or fundamental unit that we have, and I hope we already know this. We'll brush through. Length has what? Unit of meter, the mass of kilogram, time of seconds. Remember, we'll be using all this in our activities and on our calculations. Temperature in Kelvin, and that. And what are prefix? So prefix help us to simplify our what? Digits. For example, if I want to write 2000 what? Newton, I can just simply write 2 kilo Newton. Are we good? So 20, so something like this, I can just go straight forward to write 2 mega Newton, which is very what? Simple. Very good. So prefixes are used to simplify our digits so that, but remember, any engineer that you write this will understand how you mean and your answer will be correct. So let's stay with prefix and know how to use them. It's very what? Necessary. Very good. Let's look at some basic terminologies in thermodynamics. So I'll be using some terms and you should be understanding them. System. So anytime you hear of a system, what does it mean? It is defined as a quantity or a region in space chosen for study. It can be closed or open system. Anything under study. So when I choose a portion like this to study, so the 4 corners, this becomes what? My system. Are we good? Anything I want to study the particles, what is happening inside this, and the whole thing becomes my system. So if I want to study one particular human body, the entire body becomes what? The system. If I want to study Ghana, the entire country now becomes what? My system. Hope it's clear. Surroundings. What does it mean? This refers to the mass or region outside the system. So as I chose this as a system, anything outside it is what? My surrounding. So let's look at this rock. The system is the rock because I'm studying the rock, and anything outside this red line becomes what? The surrounding. Are we good? Becomes my surrounding. Boundary. This is the real or imaginary surface that separates the system from the surrounding. Are we good? The boundary of a system can be fixed or what? Movable. So when we talk about boundaries, very simple. Anything, an imaginary or a real surface that separates the surrounding from the system becomes what? My boundary. Are we good? So this rock is being what? As a system, this red line serves as what? Our boundary. It can be real or imaginary. Real means it is there, and imaginary means we assume it to be what? To be there. We will see diagrams and examples that depicts real or what? Imaginary boundaries. And this boundary can be fixed or movable. Yes. In some systems, the boundary is fixed. Others too has movable boundaries. We will look at that. And a boundary has zero thickness and can neither contain any mass nor what? Occupy volume. During our analysis, we will assume that any boundary we have, no matter the size, will have what? Zero thickness. And zero thickness means that no mass and no what? No volume. Let's put it in mind. We will not count our boundary as part of what? The masses, unless it is being what? Asked, or we are asked to what? Include it. And it's very what? Simple. Now, a system. So let's look at what a closed system is. A system can be closed or is called control mass. This contains a fixed amount of mass and no mass can cross the boundary. So when we talk about a closed system, it's a system which has a fixed amount of mass and no mass can cross the boundary. This last statement is very necessary. No mass can cross the boundary. So let's look at this system. Are we good? So we can see that this system, this is it. Every system or everything inside it is very closed. They are closed. Look at, we have a boundary here, there's a boundary here, there's this boundary and what? The downward boundary. Meaning no mass is going to what? Get out. But energy, yes. There's a difference between the mass and what? The energy. So the energy can be in a form of what? Heat energy. Heat can get out, yes. But for the mass to get out so that we can get a reduced mass in closed system, it is no. Are we good? And this has what? A fixed boundary. Let's look at it here. This one has what? A fixed boundary. The boundary is what? Fixed. No movement. It has a fixed boundary. Are we good? All right. So the mass cannot cross the boundaries of what? A closed system, but energy can. We will explain much and you understand why energy can. Are we good? In the case of a closed system, remember a closed system has no what? Mass movement outside of what? The system. Where even energy cannot cross the boundary, the system is said to be what? Isolated. There are some, remember I said in this closed system, the mass will never get out, but energy can. But there are some closed system where mass will never come out, energy will also not come out. And that system is called what? Isolated. Isolated what? System. But in reality, there's no 100% what? There's no 100% isolated system. Are we good? One way or the other, a small amount of energy may come out, but we assume it to be what? 100% what? Isolated, meaning no mass, no energy. And it helps us to what? Make other deductions. We will get more understanding when we try to dive deeper. Open system. So we saw that the closed system is also called what? What? Control what? Mass. And we have open system. It's also called control volume. So what is an open system? This encloses a device that involves mass flow such as what? Compressor, turbine or nozzle. Both mass and energy cross the boundary of a control volume or an open system in the form of heat and work interaction. So open system is just the opposite of closed system. With open system, both mass and energy come out from what? The system. They what? Come out. So they can cross what? The boundaries, meaning no restriction. Are we good? The boundaries of a control volume are called what? Control surface, and they can be real or what? Imaginary. So let's look at this cylinder and piston. This is what? A space where the mass inside this can come out. So there can be a flow in or a flow what? Out. There can be an out, there can be an what? In of what? Mass. And that makes it what? An open system. Because mass can get inside it and mass can come out, it is called what? An open system. Are we good? These two, we have the boundary, it's like a pipe, a nozzle, and there is what? Mass coming in, the same mass will what? Come out. So the ability for mass to come in and mass to come out makes it what? An open system. Are we good? And looking at this, the boundary is real. We can see the boundary over here. It has a boundary. But this is more like a pipe. There's water going inside and coming out. But if I'm studying this, I will assume there's water boundary. And this boundary, which is not seen, but assumed, is now what? An imaginary what? Boundary. Are we good? So the difference between the imaginary and the real boundary is that for the real boundary, you can see it. But the imaginary, we assume it to be what? To be there. Are we good? Look at this. Property of a system. Property of what? A system. A property of a system refers to any characteristics of what? The system. So if I have a particular system, all the characteristics of the system becomes its property. Are we good? The behaviors of the system, how it changes with respect to temperature, with respect to pressure, they are all what? The properties of the system. And some common properties are, so anytime we talk about properties of a system, the common ones are pressure, temperature, volume, and mass. So we can include other viscosity, thermal conductivity, modulus of what? Elasticity. They are all properties of a system. But these properties are grouped into two. We have what we call intensive properties and we have what we call extensive properties. With thermodynamics, they are very easy. One is always the opposite of the other. When we talk about intensive properties, these are properties which are independent of what? The mass. They are independent, meaning let's assume this is what? Water. This system is full of what? Water. And the properties we are considering is the mass, the volume, the temperature, the pressure, and the density. When we say the intensive property, it means that it is independent of the mass. So let's assume this is a 10 kilogram mass water. If I want to know the intensive property, if I divide this into two, the properties at half must be equal to the properties here if it is what? Intensive property. So for example, the temperature, if this is at 120 degrees Celsius temperature, if I still divide it, this temperature will still be 120 degrees. This will be 120 degrees Celsius. Are we good? Meaning temperature is what? Independent of the mass. Even if I choose a small amount of mass here, the temperature will still be 120. Are we good? What about the pressure? If I choose a small amount, the pressure in this small amount will still be the same as the entire pressure. The same thing happened to what? The density. If this density is what? 1 kilogram per what? Meter cube, I choose a very small amount, the density of water here will still be the 1 kilogram per what? Meter cube. So intensive properties are properties which are independent of mass. No matter the amount of the mass, the properties does not change. They are very simple. Some include the temperature, the pressure, and the density. What about the extensive properties? These properties are what? Dependent on the size of the system. They include the mass, the volume, and the momentum. Are we good? So let's assume the same thing. I have this water and it has a volume of what? 20 what? Meter cube. If I now divide it and choose phase 1, the volume will decrease to what? 10 meter cube, meaning this volume property depends on the mass. So volume is what? Dependent, and it is what? An extensive property. If this is what? A 20 kilogram what water and I take a small amount of it, this will never be what 20 kilogram. It can be 5 kilogram. And since it has what decreased depending on the mass has also become what an extensive property. The same thing happens to what the momentum. So extensive properties are properties which depend on the mass. Intensive does not depend on the mass. Very simple. An extensive property per unit mass is called specific property. Put this in mind. Any extensive property per unit mass is called the specific of the what? Property. Are we good? Specific property. So if I have volume per mass, then the volume becomes what? The specific what? Volume. Are we good? Anytime I have that, that will be okay. Generally, uppercase letters are used to denote extensive properties except mass, and lowercase are used to what? Denote intensive properties except temperature and pressure. We must put that in mind. The continuum assumption. As we are studying thermodynamics, we have what we call the continuum assumption, which is very what? Necessary. Matter is consists of atoms that are widely spaced in the gas phase, yet it is very convenient to disregard the atomic nature of what? A substance and view it as what? Continuous. So the continuum assumption, what it means is that always when we are studying anything, we assume it to be what? Continuous, like a chain form. Are we good? When I take molecules of gas, they are separated. Are we good? But when I want to study, I have to put it in mind and assume that these particles are what? Together. They are continuous. They are not separated from what? Each other. And that's what we call what? The continuum assumption. It's help us to what? Know the behavior of what? Properties or what? Matter. Very simple. Because if I'm to study this, the particles, the behavior of each particle by one, I have to focus on this later, come on this later, and know them one by one. Are we good? But now, if I consider them to be continuous, they are continuous, meaning the behavior of this is the same as the other, is the same as the other, is the same as the other. And it will help me to what? Make what? Analysis throughout. So this is what we call the continuum assumption. We assume what? Properties or matter to be what? A continuous property. And this will help us. We will tackle the next basis or fundamentals in the next episode.